NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is now more mysterious and beautiful than humanity's dreams. Biden has introduced the first image to be shown publicly from the James Webb Telescope. Since telescopes can gather more light than the human eye can see, they have improved our ability to see the stars. Numerous pieces of equipment have been developed throughout the years to further our understanding of space, but none have achieved the kind of advancements that the James Webb Telescope has. It has been demonstrated that this telescope can travel back in time to the universe's beginning. Everything changes now that we have the official clearest photograph of the City of Lights ever seen. 18 different images, one per each mirror, are what we anticipate. Come discuss this astounding new finding from the James Webb Telescope and its potential implications for the future. This is no typical telescope. This masterpiece of human invention is the biggest and most potent space telescope ever constructed, and its goal is to transform our knowledge of the universe. Scientists are able to travel back in time to a moment when the cosmos was just 200 million years old, thanks to the state-of-the-art equipment of the JWST. We shall be able to turn back time in the universe with the help of this invention's information. In addition, the telescope can take pictures of some of the oldest galaxies that ever existed, displaying the first stars in the universe gleaming in the pitch-black cosmos. NASA declared that the James Webb Space Telescope would study 4 primary topics when it launched: the first light in the universe, the formation of galaxies in the early universe, the emergence of stars and protoplanetary systems, and planets, including the origins of life. These goals have been difficult to achieve because of the challenges in getting clear views of space, yet they are essential for the study of space. As a result, it has been crucial to figure out how to collect as much information as possible and then use the best brains to evaluate the data. Critical science and calibration tests were conducted on the telescope prior to it starting its astronomical observations. The sun shield, a sizable 5-layered fabric that shields the telescope's delicate instruments from the sun's heat and light, was deployed during one of the most significant tests to guarantee that every layer was correctly tensioned and aligned. This deployment needed to be carried out precisely. Any misalignment or damage to the sun shield could make it difficult for the telescope to see far-off objects. Fortunately, it passed this test and advanced to the subsequent one. The telescope itself needed to be deployed next to provide a sharp image. The 18 hexagonal segments that make up the JWST's primary mirror had to be precisely aligned. This procedure comprised slowly deploying the primary mirror, extending the telescopic support structure, and unfolding the sun shield. The mirror needed to be precisely aligned for scientific observations after it was fully deployed. Even the smallest error would be equivalent to throwing away more than $1 billion. To make sure all of the telescope's scientific instruments were operating properly, another crucial calibration test entailed turning each one on individually. These instruments, which have different capacities for studying the cosmos, are the mid-infrared instrument, the near-infrared spectrograph, and the near-infrared camera. Lastly, the telescope needed to be accurately positioned in space to view its target objects. To make sure the telescope's pointing and tracking systems were aimed at the right targets, this procedure, known as commissioning, required monitoring calibration targets to ensure the JWST was in good operating order and prepared to start its mission of exploring the universe. All of these tests were essential. The scientific community was growing increasingly excited as these intricate operations were carried out successfully. The JWST was passing every test with flying colors, which was incredible. The JWST project involves almost 300 colleges, organizations, and businesses from 14 nations, as well as 29 U.S. states, making it a truly global endeavor. After passing every test that NASA could throw at it, the James Webb Space Telescope was officially cleared to start its amazing scientific mission in July of 2022. NASA said that the JWST was prepared to begin its exploration mission after all 17 of the observatory's scientific instrument modes had undergone thorough testing. The main function of the JWST, like any other telescope, is to gather light and focus it so that we can see distant objects. Nevertheless, the region of the electromagnetic spectrum that the JWST views distinguishes it from other telescopes. The JWST sees in what is similar to the heat-producing infrared spectrum, whereas human eyes only detect visible light. Consider it the cosmos equivalent of a high-tech surveillance camera with night vision. Smaller and farther-off objects can be seen thanks to the JWST's ability to gather even more light than conventional telescopes due to its vast size. Furthermore, because it is in space, it is not affected by atmospheric interference, which can obscure important data, giving it the moniker "Eyes on the Universe." The enormous 21-foot mirror on the JWST collects light and reflects it back to the spacecraft's instruments. It features 4 devices, each designed to catch a distinct kind of light and offer a distinctive perspective on the cosmos. The primary camera, the near-infrared camera, is used to take breathtaking pictures of far-off galaxies, nebulae, and other celestial wonders. By dissecting light into its individual colors, the near-infrared spectrograph can provide additional details about the items it is studying. With the purpose of capturing infrared light, the mid-infrared instrument aims to investigate the early cosmos, exoplanets, and our own solar system. Lastly, the near-infrared light-sensitive fine-guidance sensor, near-infrared imager, and slitless spectrograph are used for precise pointing. Because infrared radiation has longer wavelengths than visible light, this is also made possible by the JWST. Because of their beauty and scientific significance, these photos generated a great deal of excitement and enthusiasm. The examination of the atmosphere of WASP-96b provided insights into the mechanisms guiding the birth and evolution of exoplanets, while the JWST's view of Stephan's quintet yielded fresh information about the interactions within the galaxy. The first JWST science quality image was unveiled on July 11, 2022, by NASA Administrator Bill Nelson, Vice President Kamala Harris, and President Joe Biden. Using just 12.5 hours of viewing time on one of the telescope's 4 instruments, this image represents the deepest infrared view of the universe to date. NASA declared in February 2022 that the JWST had taken its first pictures of stars. The star HD 8446 was represented by a mosaic of 18 dispersed brilliant spots. Thomas Zurbuchen, NASA's Associate Administrator for the Science Mission Directorate, stated on Twitter that these 18 dots would eventually merge into a single star when Webb aligns and focuses. This significant achievement illustrated the telescope's capacity and possibilities for future research. In the ensuing weeks, Webb's advancement persisted. NASA unveiled an enhanced and fresh photograph of HD 8446 on February 18th. The observatory purposefully arranged the 18 unfocused copies of the star into a hexagonal shape to provide a better representation of the final image. After the various parts of the primary mirror were correctly aligned, scientists were able to obtain a clearer, more detailed picture of the star as a result of superimposing 18 photos over one another using a specialized camera built inside the NIRCam device for alignment and technical purposes. Webb also captured a unique selfie. Since just one mirror segment was successfully aligned and aimed at a star at that particular moment, the image revealed that section to be blazing brighter than the others. One by one, the remaining mirror segments were all correctly aligned, demonstrating the remarkable accuracy and precision of the telescope. Peering deeper into the Eagle Nebula, with its enormous columns of gas and dust reaching into space, was one of the telescope's greatest discoveries. Although it was able to capture the structure's magnificence, the Hubble Space Telescope was unable to reveal their secrets. The pillars of creation in the Eagle Nebula are home to hidden creation that has been revealed by the James Webb Space Telescope's infrared imagery. Webb's most recent snapshot revealed a large number of protostars as tiny red dots on the pillar's murky background. Stars are born in these vast agglomerations of gas and dust, each many times larger than our solar system. These young stars are not yet consuming hydrogen, according to Derek Ward-Thompson, Dean of the University of Central Lancaster School of Natural Sciences in the United Kingdom. The center gets denser over time as more material falls in, and it eventually becomes hot enough to burn hydrogen in the middle of a cosmic firestorm. Scientists can now comprehend how stars are born thanks to this image, which marks a turning point in the quest to understand how we got here. The Southern Ring Nebula, also known as the 8-burst nebula, is another object that Webb observed. This nebula is a massive shell of gas and dust that was expelled by a dying star and is located approximately 2,000 light-years from Earth. The JWST picture of this nebula revealed fresh characteristics that Hubble had missed, including 2 stars at its center rather than just one, the second of which is surrounded by dust. This finding offers information about how stars develop and their ultimate demise. The JWST, however, has also produced some unsettling and enigmatic discoveries. The discovery of 6 massive galaxies in the universe's early history, when it was only 500 million to 700 million years old, was one of the telescope's most perplexing results. These galaxies' tremendous mass indicates that they formed far more quickly than our current understanding of galaxy creation allows. These celestial giants question the Big Bang Theory's current predictions and cast doubt on our understanding of how galaxies develop. NASA's decision to name the James Webb Space Telescope, JWST, after its former administrator in 2002 was contentious and divisive. Webb was hailed for his management of NASA during the Apollo mission, yet some members of the public were outraged that he had a part in the persecution of LGBTQ+ individuals during the Lavender Scare. The naming of the JWST was contested by many astronomers and other members of the scientific community. There was a backlash from both inside and outside the scientific world. Those who objected to the JWST name suggested giving it a new name that would be more in line with the fundamental values of astronomy, which emphasized the virtues of objectivity, fairness, and inclusivity. However, NASA has continued to call it the JWST. These various events help illustrate how complicated and nuanced the process of creating and launching a space telescope is. They also illustrate how difficult it is to use the findings that it produces. The James Webb Space Telescope, JWST, is a revolutionary marvel in the field of astronomy, designed to push the boundaries of human understanding of the universe. Its development spanned over 2 decades, involving intricate engineering and international collaboration, with the goal of exploring the cosmos in ways that were previously unimaginable. Launched on December 25, 2021, from French Guiana, this space telescope was positioned at the second Lagrange point, L2, a stable location approximately 1.5 million kilometers from Earth, where it orbits the Sun in harmony with our planet. This location allows the JWST to maintain a stable temperature and unobstructed view of the universe, which is critical for its mission to observe the faintest and most distant objects in space. One of the most groundbreaking aspects of the JWST is its ability to observe the universe in the infrared spectrum. Unlike visible light, infrared light can penetrate clouds of gas and dust that obscure many celestial phenomena, allowing the JWST to peer into regions of space that were previously hidden from view. This capability is particularly important for studying the early universe, as light from the first galaxies has been redshifted into the infrared due to the expansion of the universe. The JWST's primary mirror, which is 6.5 meters in diameter and composed of 18 hexagonal segments, is designed to capture this ancient light with unprecedented clarity. Each segment is made of beryllium and coated with a thin layer of gold, optimizing the mirror for reflecting infrared light. In its first year of operation, the JWST has already delivered on its promise to transform our understanding of the cosmos. One of the most striking images captured by the telescope is the Deep Field View, which reveals a section of the sky teeming with thousands of galaxies, each containing billions of stars. This image, known as the Cosmic Cliffs, offers a glimpse into the universe as it appeared billions of years ago, just a few 100 million years after the Big Bang. The level of detail in these images is staggering, with structures as small as individual star-forming regions visible in distant galaxies. The JWST has also made significant strides in the study of exoplanets, planets that orbit stars outside our solar system. By analyzing the light that passes through an exoplanet's atmosphere, the telescope can determine its composition, temperature, and even the presence of potential biosignatures such as water vapor, methane, and oxygen. This capability represents a significant advancement in the search for life beyond Earth, as it allows scientists to study the atmospheres of exoplanets in detail for the first time. One of the first exoplanets studied by the JWST was WASP 96b, a gas giant located about 1,150 light-years away. The telescope's observations revealed the presence of water vapor in the planet's atmosphere, a discovery that provides crucial insights into the formation and evolution of planetary systems. The telescope's ability to observe the infrared spectrum has also provided new insights into the life cycle of stars. The JWST has captured stunning images of stellar nurseries, regions of space where new stars are born from clouds of gas and dust. These images reveal the complex interactions between young stars and their surrounding environment, including the powerful winds and radiation that shape the formation of planetary systems. In the famous Eagle Nebula, the JWST has revealed the intricate details of the pillars of creation, towering columns of gas and dust that serve as incubators for newborn stars. The telescope's observations show how these structures are slowly being eroded by the intense radiation from nearby massive stars, offering a dynamic view of the ongoing process of star formation. In addition to studying the birth of stars, the JWST has also provided new perspectives on the end stages of stellar evolution. The telescope's infrared capabilities have allowed scientists to peer through the thick clouds of dust that surround dying stars, revealing the complex structures of planetary nebulae, shells of gas and dust ejected by stars as they exhaust their nuclear fuel. One of the most spectacular examples of this is the Southern Ring Nebula, where the JWST's observations have uncovered intricate details of the nebula's structure, including previously hidden companion stars that may have influenced its shape. These observations provide valuable information about the processes that govern the final stages of a star's life and the formation of the elements that are essential for the existence of planets and life. The JWST mission is not only to study individual objects in the universe, but also to address some of the most fundamental questions in cosmology. One of these questions is the nature of dark matter and dark energy, which together make up about 95% of the universe's mass energy content. Although dark matter and dark energy cannot be observed directly, their effects on the universe's structure and expansion can be studied through the observation of galaxies and galaxy clusters. The JWST's ability to observe the distant universe in the infrared allows it to study the distribution of dark matter in the early universe by analyzing the gravitational lensing effect, where the gravity of a massive object like a galaxy cluster bends and magnifies the light from background galaxies. This provides crucial data for understanding the role of dark matter in the formation and evolution of cosmic structures. Another area where the JWST is expected to make groundbreaking discoveries is in the study of the first stars and galaxies that formed after the Big Bang. These objects, known as Population 3 stars, are thought to have been composed almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. The light from these stars has been traveling through space for more than 13 billion years, and by the time it reaches Earth, it has been stretched into the infrared spectrum. The JWST's infrared sensitivity and large mirror make it uniquely suited to detect this faint light, providing direct observations of the earliest stages of star formation in the universe. These observations will help scientists test theories about the formation of the first stars and galaxies and gain a deeper understanding of the origins of the cosmos.